So here we have got the final expression of our velocity profile, that is v theta of r is given as omega naught upon 1 minus kappa square into r minus kappa square r square upon r. So this is our final expression. So let us plot this and understand the curve in pictorial manner. So here, as you can see on the screen, we have plotted the velocity profile in coaxial cylinders, that is tangential flow. Here the flow is being started at the red wall, and at the red wall the velocity is 0. Here red dash line indicates the inner stationary cylinder, that is at r is equals to kappa r, and the blue curve represents the velocity distribution as derived, and the green dashed line represent the outer rotating cylinder, that is at r is equals to r with the angular velocity omega naught. So as you can see, our expression is, one term is linear and the other term is inversely proportional. So the curve indicates that both the behavior. It is not a linear curve, it is a non-linear curve, and it is showing both the nature, that is linear, and the inversely proportional, both both the natures. So here the key observation which we can observe, that is velocity is 0 at the inner cylinder, that is r equals to kappa r, because the inner cylinder is stationary. The velocity reaches maximum at the outer cylinder, that is at r is equals to r. Their velocity becomes v theta is equals to omega naught r. And the third key observation is that the velocity increases non-linearly, influenced by both linear and inversely proportional. Or you can see this flow more in detail through this picture, where you can understand it. In this picture, you can see this arrows which are showing the velocity profile equation. This is a top view of the two coaxial cylinders. Here the inner cylinder is representing, which is of radius kappa, and the outer cylinder is of radius r. And as you can see, these arrows are representing the velocity profile equation. So at the wall of inner cylinder, the velocity is 0. At the wall of the outer cylinder, the velocity is maximum and is equals to omega naught r. So this picture clearly represents our velocity profile equation.
So now let us come to the physical interpretation of the velocity profile in coaxial cylinders. So we derived an equation which is v theta r is equals to omega naught by 1 by kappa square into r minus kappa square r square upon r. So this equation describes how the fluid rotates in annular gap between the two cylinders. Again now we will break down this into several different parts in different regions to understand what happens at various locations. So first, velocity at inner cylinder where r is equals to kappa r. So similarly, we have to put the value r is equals to kappa r in this equation. So we get v theta kappa r is equals to omega naught by 1 minus kappa square into kappa r minus kappa square capital R square upon kappa capital R is equals to 0. So what's the physical meaning of it? The inner cylinder is stationary, which is a boundary condition, and the fluid adjacent to the inner wall is also at rest due to no slip conditions, as we know. So this means the fluid is dragged by viscosity but cannot move at inner boundary. Okay. Now secondly, velocity at outer cylinder where the value of small r is capital R, like r is equals to r. So again we substitute that in the equation. So we get v theta r is equals to omega naught by 1 minus kappa square r minus kappa square r square by r is equals to omega naught r. Again we come to the physical meaning. So the outer cylinder rotates with angular velocity omega naught, and due to no slip condition, the adjacent fluid layer moves at the same velocity as the cylinder. So thus maximum velocity occurs at the outer wall, right? Now thirdly, the velocity distribution in angular region, where r lies between kappa r to r. So the general form of this is given by v naught r is equals to a r plus b by r, where the first term ar represents the solid body rotation component, and the second term b by r represents the free vortex component, where the velocity decreases inversely with the radius and is also similar to rotating inviscid fluid. Again, for the first term, like the first term is air, so as whole fluid we are rotating as a rigid body, so we taking that condition here. Again, so what observations we take out from this is that firstly the velocity increases with r, so as the fluid moves faster, we move outward. So this is because the motion is reduced by the rotating outer cylinder. So the velocity is the strongest near this moving boundary. Secondly, as you know, here velocity is non-linear. So unlike the linear quarter flow between the parallel plates, the velocity profile in cylindrical coordinates follows a curve shape due to that 1 by r inversely dependency to r. Again, thirdly, the viscous shear effects. So what are these? The presence of viscosity ensures that the fluid at the inner stationary boundary at r is equals to kappa r remains at zero velocity. And again, the viscous forces transfer momentum from the rotating outer cylinder inward toward the stationary inner cylinder, and gradually showing the fluid as it moves inward. So this was the velocity distribution. Now let's come to the fourth case, the special cases of the velocity profile. So there are two cases actually. So for first case, when kappa tends to 0, like the inner cylinder is very small, so like kappa tends to 0. So if the inner cylinder's radius become very small compared to the outer one, so then v theta r is approximately equal to omega naught r. So this means the flow approaches rigid body rotation, where the fluid particle moves as if it were part of the solid disk. The second case, when kappa tends to 1, so like annular gap is very small between the cylinders. So if two cylinders are very close together, the velocity profile becomes nearly linear, similar to the plane quartic flow. So again, the equation comes as the v naught r is approximately equal to omega naught by 1 by kappa square into r minus kappa capital R. So this is similar to the velocity profile between two parallel plates, where one plate moves. Now let us come to the interpretation in terms of angular momentum. So we see that the flow has a combination of linear and rotational effects. Till now, the case we have seen, the flow has a combination of linear and rotational effects. So the term v naught is equals to ar plus b by r suggests that the fluid closer to the center has less angular momentum than the fluid at the outer boundary. So this is different. Again, this is different form of an ideal vortex flow, where v naught is inversely proportional to r everywhere. So these are some points we have observed for the angular momentum. Again, sixth case, energy and shear stress analysis. So what is this? Firstly, the kinetic energy considerations. So the kinetic energy per unit volume is proportional to v naught r of v theta square. So this is the highest near an outer rotating cylinder. The energy where it is the energy there is highest near the outer rotating cylinder. And secondly, the energy gradually decreases toward the inner cylinder due to viscous dissipation. Right. So energy decreases towards the inner cylinder. Right. Now the shear stress, tau. So the shear stress in a Newtonian fluid is given by tau r theta is equals to mu dv naught by dr. This is the equation which we give to shear stress, which is tau. So since here the V naught is a non-linear function of R, as we can see, the shear stress varies across the annular region. Okay, and the maximum shear occurs near the inner cylinder because the velocity gradient is steepest there, right?
So now, as we have understand the whole problem and its situation, its velocity profile, we have derived everything. So let us understand its real-world application in fluid flow. So the first application is in journal bearings, lubrication in rotating machinery. So application is journal bearings are used in engine, turbines, compressor and electric motors to reduce friction between rotating shafts and stationary housings. These bearings rely on thin film of lubricant, oil or grease to separate the moving part. How the coaxial cylinder flow is involved. The inner shaft journal stationary and the outer casing bearing rotates, creating shear driven flow in the lubricating film. The velocity profile in the lubricant follows the coaxial cylinder flow model which we have studied just now, ensuring a smooth rotation and minimizes the wear. Viscous forces in the lubricant prevent direct contact between the metal surfaces, reducing heat and friction. Examples are automobile engine. The crank shaft rotates inside the journal bearing lubricated by engine oil. And other example is wind turbine. Bearing inside rotating component use similar lubricant to handle high loads and speeds.
So the other application is Taylor-Cote flow, which is related to the flow instabilities and mixing in research and industry. So let's come to the application. So when both the inner and outer cylinder rotate, or when one is stationary and the other rotates at high speeds, the flows transition from laminar to Taylor-Cote flow, forming circular vortex structures. So this is used in first scientific research for fluid stability and turbulence studies. Secondly, industrial mixing regarding the chemical reactors in the chemical reactors, and geophysical modeling, which is related to the planetary atmosphere. Again, how the coaxial cylinder flow is involved here. So at low rotational speeds, the flow remains laminar and following the basic velocity profile which we derived earlier. And at higher speeds, centrifugal forces create vortices which enhances the mixing. So let's come to the examples. So firstly, as we discussed, in chemical reactors, used for control mixing of liquids without external stirring, and weather modeling. Secondly, where it is used to study how atmospheric layers move around planets.
So thirdly, the one of the important application is in the rheometers for measuring fluid viscosity in laboratories and industries. So application of rheometer that it is used to measure the viscosity and flow behavior of fluid in food products, honey, ketchup, dairy, or in pharmaceuticals, in syrups or gels, in polymers and paints, then non-Newtonian fluids. So, how this is involved in the flow? The outer cylinder rotates while the inner cylinders remain stationary, or vice versa. The measured torque and the velocity distribution give the precise values of viscosity, fluid resistance to shear. Example: paint industry ensures correct thickness for spray coating, and dairy industry determines cream or yogurt viscosity for quality control.
So again, another application we have as oil extraction and transport, particularly in pipeline and wellbore flows. So as we see, oil wells and transport pipelines often have multi-phase flow, like oil, water and gas, that behaves like coaxial cylinder system in some cases. So like first, the drill pipe, the inner cylinder, is stationary while the oil flows in the annulus around it. Again, the flow can be shear driven, like the viscous drag from the surrounding pipe walls. So again, how the coaxial cylinder flow is involved here. So wellbore drilling, firstly, where the drilling mud flows between the drill pipe and borewell wall. again the crude oil transport. So like in coaxial pipeline systems, one fluid, for example, let's take water, flows in annulus while other we take as oil flows in the another pipe. So the example we have like in oil refineries used in various heating systems where hot fluid flows in annulus to keep the oil from solidifying.
Similarly, the fifth example is biomechanics, that is the blood flow in arteries and veins. So, when the blood flows in arteries, especially near the stents and artificial grafts, mimics coaxial cylinder flow. The inner artery wall is stationary. The outer layer, blood plasma, moves faster due to heart's pumping. The velocity profile varies across the annulus between the arteries and the wall. So, how the coaxial flow is involved? The blood viscosity and the shear stress influence cell transport and plaque formation. And artificial blood vessels use coaxial design to optimize flow and reduce turbulence. Example is stents and grafts improve blood circulation in blocked arteries.
So again coming to another application, we have electric motors and generators in cooling and rotating machines. So like the electric motors, generators and transformers use cooling fluids in the annular space between rotating parts and stationary casings. So how the coaxial cylinder flow is involved here. So the rotor, which is the motor or the rotor in the inner cylinder, spins, generates the heat. Secondly, the fluid, we can take like oil or air, circulates in the annular gap to remove heat. So example, in wind turbines and power plants, it prevents overheating in high-speed motors.
In centrifuges, medical and industrial use, centrifuges are used in blood separation, plasma versus red cell, chemical processing, and wastewater treatment. How the coaxial cylinder flow is involved? The outer cylinder spins rapidly, creating a strong velocity gradient in the annular fluid. Particles separate based on the density and viscosity effects. Example in medical labs, used for DNA separation and blood tests.
Yeah. And again, it has also an application in submarine and ship propulsion, where in fluid bearings in rotors, which are at the rear end of the ships. So in high performance naval and submarine propulsion systems, the fluid film bearing help reduce friction and wearing in rotating shafts. So again, how the coaxial cylinder flow is involved here, as the seawater or oil is used as a lubricant in the annular gap between the shaft and bearing. Again, the velocity profile follows the coaxial cylinder model, ensuring the smooth rotation. So for example, we can see nuclear submarines where the use water lubricated bearings to maintain silent operations. So now let's come to the conclusion that why coaxial cylinder flow is important.
So, as we have learned all the application in details, so we can conclude through the points that the coaxial cylinder flow is important because this is a widespread application in engineering, industry, and natural sciences. It is critical for lubrications, that is, bearing in engines and machineries. It is for mixing and in chemical reactions, like the Taylor-Court flow in reactors that we have discussed in our problem. In the measurement and quality control, rheometers in food, paint, and pharmaceutical industry. In energy transport, oil extraction, cooling, or in electric motors. In medical or biological systems, blood flow or centrifuge. In naval and aerospace application, fluid bearings in ships and submarines. And there are more number of applications which are far using the coaxial cylindrical flow, the coed flow, and that concept is being applied and being used in that application. So we hope that you have learned the coed flow of the two coaxial cylinders in details and understand all its detail, its velocity profile, its derivation, and its application.
So hope you enjoyed the session. So again, let's meet in another episode for such interesting topics. Thank you.